Oh, well, hello, my name is Robert Javier, and I'm here presenting with Haley and Contran. We're presenting for the Sensor Pallet project, the Drone Modular Smart Pallet. So, our goal is to implement a smart drone pallet integrated with various sensors to collect and process real time flight data. The data is also to be utilized in an object detection and collision avoidance algorithm for the urban air mobility mission. To ensure the practicality of a relatively new project, we impose some constraints to be maintained. Some of these constraints include the pallet should be moving at 5 meters per second at most, should be a standalone system weighing no more than 15 pounds. It should be low cost, power efficient design, and have the capability to be adjusted for different types of vehicles. These are important in considering the sample rates for our sensors and how we will communicate and monitor our system. We must consider the battery capacity, along with some of the materials and design choices for a pallet to ensure that we don't exceed the weight limit. Some of our general tasks we had included are identifying appropriate sensors that are compatible with one another and interfacing them to acquire and store raw data. We also had to come up with a modular design for a pallet to house all of our sensors and microcomputers with minimal obstruction. We must use a large enough battery to sustain power for a minimum of 5 minutes. We must also integrate the sensors with one another and use them for obstacle and collision avoidance.
So up on the screen right now is our prototype for the pallet. So the pallet was designed to be adaptable for various drones by using swappable plating and inserts. It is also dimensions to fit under the working area of multiple specified quadcopters, and it was dampened for vibrational tolerances in considerations of all the electrical devices. The simulated natural frequencies that were exerted on the pallet were too low and too weak to disturb the image vital devices such as camera or lidar. Um, the estimated vibrational output from in-flight drone will have minimal sense vibrations on the pallet's place and mounting surfaces. The design allows for some impact resistance, and mounted devices would be secure during a rough landing, such as caught in a crosswind or other general landing cases. The pallet in a simulation was able to survive a free fall from about 1.2 meters, where the harm mounted devices on the pallet should also remain intact. And about the thermal camera, so the thermal camera that was used for this palette was the WaveShare MLX 90640 with a 55-degree field of view. It is a low resolution infrared camera that uses thermopile technologies instead of the usual micropolometer technologies that is usually used for like a more high-end thermal cameras. It comes with a 768 pixel array that are arranged in a 32 columns by 24 rows format, where each pixel has its own temperature values assigned to it. The display frame from the camera outputs the minimum and maximum temperatures based off of the average that are in the camera field view. It communicates with the microcomputer through I2C. Some of its uses are to measure a target temperature and recording the thermal imaging data. And when this is accomplished, sensor fusions would be our next objective.
Our next sensor on our palette would be the NOIR Pi Camera V2. The V2 NOIR Pi camera is equipped with the Sony IMX219. This is an 8 megapixel image sensor that has a fixed focus lens and will be mounted near the front of the pallet. Originally dedicated for object detection and stereo vision distance measurements, one Pi camera will be primarily used for object detection. No infrared filter version of a Raspberry Pi camera will give off a pink hue during the day, but will also provide better vision clarity during low light scenarios. The Pi Cam can be paired with a Google Coral USB accelerator. This will ultimately direct the main processing of the Raspberry Pi or from the Raspberry Pi's CPU to the Coral to help improve frame rate issues. This figure shows an object detection alongside with other related tasks. So the first stage is classification, and it specifies the label of the object or what class it belongs to. Localization will find the bounding box around the object. Um, Object detection has both classification and localization and is used for multiple objects within the image frame. Segmentation takes the most amount of processing power and will not be used within our project, but it outlines the detected object within image frame. Deep learning object detection methods can be categorized into one-stage and two-stage detectors. Two-stage detectors have an extra step, which is the region of interest pooling layer. One-stage detectors propose predicted boxes directly without using the regional proposal step. The one-stage detectors are time efficient and are used for real-time devices. We will be implementing a one-stage detector to minimize the computational time of object detection. So, why do we need object detection? Object detection allows the drone to make more informed decisions when it comes to collision avoidance. Ultimately, identifying the object will make it easier to maneuver in a dynamic urban environment. In data collection cases, the Pallet can be used to perform certain objective-driven missions or survey tasks. Next off, we have the RaspberryPi. The RaspberryPi camera will be part of our future work. The synchronized camera captures objects simultaneously, and a code will be written to take distance and angle measurements of a detected object within frame. The original NOIR Pi cameras could not capture footage simultaneously, which eliminated the possibility of the stereo vision objective. The synchronized cameras are optimized for stereo vision and will be much more accurate for taking measurements for object detection.
Next, we have the GPS. The GPS will be used to calculate the location of the drone. It does this by receiving signals from satellites. These signals contain the time that it was sent from the satellite. The receiver then compares it to the current time to calculate the distance. By doing this with many satellites at a time, a more precise location can be found and put into the coordinates that can be mapped. This will be used to find the location-specific data and possibly even trends found in similar flight paths. We also have the IMU. The IMU receives information on the forces acting on the drone, which can tell the orientation of the drone, its angular rate, and the cardinal direction that it is facing. It does this by utilizing triple-axis micro-electromechanical systems to read these forces. The accelerometer and gyroscope MEMS have configurations of variable capacitors and springs that allow a center mass with the capacitor plates to move. Reading the voltage changes gets the forces acting on the drone. For the magnetometer, voltage is read across the sides of a plate with a current flowing through it. The voltage reading is used to calculate the magnetic field it senses. The IMU can be used to see limitations on the pallet, outside forces, and finding the cardinal direction. The next sensor is the Lidar. The RP Lidar is one of the more complex sensors on the pallet. It transmits a light signal, and based on the offset of the reflected signal, it calculates the distance. The data is received in angles and distances, and it is able to cover 360 degrees on a 2D plate. It's capable of working in a bright outdoor environment with a range of 40 meters. The sensor is used to cover blind spots, verify range of objects detected by other sensors, and avoid collision. The future plans for this sensor consists of mapping and localization. And next we have the radar, which is kind of similar to the LiDAR. This one works by sending and receiving electromagnetic signals instead of infrared. And the big difference is that the radar has a range of 100 meters, but has a much smaller field of view and only sees directly in front of the drone. The radar is also able to detect objects and will be used for collision avoidance, but it can also read the speed of an object moving near the drone.
So our next goal for this project would be, first of all, software integrations, then sensor fusions using ROS, which is a robot operating system, and then start producing prototype Pallet and then finalize Pallet. testing in a control environment and then test those obstacle avoidance algorithms.
Thank you. Any questions?
Okay, thank you. Yeah, so you finished about 2 minutes early. So we can begin the question and answer session. Do the judges have any questions?
Yes,
Yes.
I will start
Oh,
with a question. So in the last slide, you talked about software integration. Uh, can you tell us a little bit more about what platform, what software, what does it integrate with, please?
So ultimately, our software integration is kind of paired along with our sensor fusion aspect. By software integration, we necessarily mean so we have the codes, specific codes for each of the sensors, and ultimately we want to kind of combine the functionality of each sensor so it kind of covers all ranges of aspects of different data testing when attached to the palette. So we actually haven't gotten very far. We just started using our ROS system, but we want to set up a single node as our main uploader or publisher, and then have different subscriber nodes to deliver and receive information between different sensors so that it kind of pairs together.
Okay, thank you.
the question, I have actually 4 questions. First of all, related to, this is Vaughn Cable, related to the last question, what language are you programming all of these and integrating all of these things in?
So part of our sensors are being programmed within Python, and another part are being used in C++. And I think that's part
Okay.
of the reason why we're choosing ROS, because it allows for integration between both languages.
Great. Okay. Now, just one thing I wanted to say is that a comment in it to rest assured that infrared or IR and electromagnetics, they are the same thing. They're not different. IR is electromagnetic waves. So it's just a different wavelength. And just to make that point for you guys. Okay. Why the magnetic fields? What in the IMU? What are the magnetic fields telling us? The magnetometer. I know we have the GPS, but the magnetometer, is there are you measuring deltas in the magnetic field? Because the magnetic field varies depending on where you are on the Earth.
Yes, I'm not actually well versed in the IMU.
We're using it to measure the orientation of the drone.
Okay, so maybe that's an approximation of the orientation. Okay, all right, I understand. At any one moment, yeah, all right.
Yeah.
Um, and what is the infrared range? Of wavelength range, not the range of how far it goes, but your infrared sensor. I think that was like the first sensor you discussed. What's that wavelength range?
The NOIR Pi camera is not equipped with an infrared sensor. It's I believe no, I passed it. So this camera itself is not. It's a no infrared filter.
Oh, the other one. We passed the slide.
The thermal.
Yeah, the thermal.
Oh,
Yeah.
sorry.
What were the wavelength limits of the wavelength?
I'm unable to answer that. But my teammates are actually present within the presentation. So if they have an
Okay.
answer,
Is it long wavelengths or short wavelengths? Do you know? There's usually a okay. Probably short.
I believe it sounds like it'd be short. I believe it'd be short.
Yeah. All right. Okay. Those are my questions. Thank you.
I have a follow-up question just from the project point of view. So is my understanding correct? This is Vijay Bhatt, that it is a one semester or 2 semester task? 1 semester, or how long it took you to come up with where you are right now? Because you started from the scratch, right?
So right now, in terms of, I'm actually unsure of how long the project has been going on. This is actually my second semester. But we have had a couple setbacks that we've needed to restart code for certain sensors. Like we have replaced multiple different sensors. So as of right now, the progress that we've made has been within one semester.
What
But this is
semester?
still a fairly
Yes.
new project. It's
It's
only
a
been
fairly
going
new
on for 3
project.
semesters.
Only 3 semesters?
Yes.
Okay.
So,
So
so unfortunately, we have to move on just for time purposes. I apologize, Dr. Bott, for interrupting.
sure, no problem.
So
Thank
you to the drone modular smart pellet and the judges and the audience. Just as a reminder, the audience can ask questions for the upcoming presentations.